Hi, welcome back. Okay, so we have one more thing to cover in the answers to the quizzes. And let me back up just a little bit before we answer that question and say a little bit about something about the rules of SD that we're currently using. And right now, I mean, we're using some really simple and basic rules, and I know to a lot of you they seem a little bit unmotivated. So let me say a little bit about something about why we're picking the rules that we are. And there's going to be sort of two reasons for that. Remember, whatever rules of SD that we pick, the primary feature that they need to have is that they need to be truth preserving. Key thing that any rule is going to have. And when we talk about the inverse rule, which I'll present in a second, we'll notice that one of the features that it doesn't have is that it's not actually truth preserving. And so this is a reason why we don't actually want to add it to our system of SD. And actually, you know what? Let me just do that right away. I'm just going to cover that, the inverse rule. So recall when we have a conjunction. Remember, we have something like P and Q, and we said by the elimination rule that you can just assume P. And the reason why this is an okay inference is because this is truth preserving, right? If that conjunction is true, then you know that each of the conjuncts have to be true. So you can actually just infer P. But you can't, so this is okay. We can give that a check mark. And actually, maybe we should do this a little bit more rigorously. So this is a schema, right? This is any sentence of P and conjoined with another sentence of Q. If you have that somewhere in your derivation, then you can assume, then you can write down the first conjunct. Or we could have also done it with the second one. We could have also written down Q. But notice that this is not the case when we have a disjunction. Right? So this little triangle here just says that this is the thing that we're going to infer based on what we have above it. And suppose we have the disjunction P or Q. Well, this turns out to be a bad rule. And why is this a bad rule? Well, because it's not truth preserving, right? Maybe Q is the thing that's true and not P, in which case there will be a truth value assignment where this is true, but the thing that we want to infer, P, is actually false. So this is not a rule that we want to have to SD because it's not a truth-preserving rule. It lets us go from truths to falsehoods. And that's not to say that, you know, logic cares about the truth. Remember, we said logic doesn't care about which premises are true. The job of logic is to just say that if you were to start with true premises, then I promise you I will never lead you to a falsehood. Now, if you give me falsehoods to begin with, I can't help you out. But at the very least, if you give me truths, I will never lead you to a falsehood. So let's think about this in the case of the inverse rule. And actually, let me just make this page blank. So we had, on the quiz, we had this inverse rule. And what the inverse rule said was, okay, suppose you have this conditional, if P, then Q. And we also had not P. Now the question is, if somewhere in your derivation you have the following two accessible to you, this conditional and the negation of the antecedent, can you then conclude or infer Q? In other words, imagine you had an argument, right, where you had if P then Q and not P. Would it be a valid inference to say not Q? And the answer is no. This is not truth preserving. Okay, and let's actually prove that why this is not truth preserving. So to show that this is not truth preserving is to build a truth table in which the premises, or these two lines, will be true, but the conclusion, right, or what we want to infer, turns out to be false. In other words, we want to find a truth value assignment where these are true, but the conclusion is false. So let's do that. Let's build our truth table. And hopefully you guys are all like, you know, super experts on this now. You know, the reason why we spent so much time on truth tables isn't because we just had to fill up time idly, but the reason why we had to actually pick them up is, is because they're going to be one of our main tools for checking for certain kinds of properties. So let me do it. Shoot. Let me do it like this. Let me do it in the usual way that we do. So we're going to have this P, 2 cases where P is true and 2 cases where it's false. And where Q is true, false, true, false. Okay, now what we want to do is we want to write out the sentences that we have. So we have the conditional if P then Q. It's a terrible looking Q, but you get the idea. And then we have as a second sentence not P, and then our conclusion is going to be Q. Now, one of the, or some of you, what you ended up doing was using another kind of check for validity, which is perfectly fine. And what you did was take the conjunction of these two sentences, made them the antecedent of conditional, and then made not Q the consequent of that conditional, and then checked to see that that conditional was truth functionally true. And that's a perfectly good way of doing this as well. But for interest of time, we're just going to do it this more basic way, which is we're going to fill out the truth values for these two sentences, and then we're going to make sure that on any truth value where these two sentences are true, that not Q is true as well. So here, hopefully I don't need to repeat this, but you know what the rules for the conditional are. So I'm just actually going to fill those out. So the only time that the conditional is false is when the antecedent is true and the consequent is false. So that's only in this truth value assignment. And not P, remember, we'll just actually flip the truth values throughout. So we get F, true, and true, because we're just flipping the truth values over here. So we know before we even think about having to write out Q that these are going to be the truth values that we actually have to look at. So here we could actually, we could spend time and just quickly fill this in if we like. But what's going to be important are these two rows here. And here, not Q, this will come out false, and here this will come out true. So to see whether or not this is a truth-preserving rule, the lines of the truth table we need to look at are these two, right? Because it's on these two truth value assignments where the premises, namely these two lines, come out true. And what we need to check for is that not Q is also true on those rows. But it's not. As you can see right here, not Q is false. So if we were to introduce this inverse rule into SD, then it would let us go from truths to a falsehood. But we said that's exactly what we don't want in our derivation system. We don't ever want to go from truths to falsehoods. That should never be a valid inference, or an inference that we allow in our system. So that's the reason why we should not add the inverse rule to our system. Okay, so now that we've kind of covered the inverse rule, let me say a little bit more about the rules in general that we're using in SD. Try to motivate them a little bit more for you, for the people who think that they're a little bit arbitrary. So we have our rules of SD, and recall that there's going to be, we have introduction and elimination rules for each of our connectives. So we have and, we have or, we have our negation, we have our material conditional, and we have the biconditional. And we haven't really said anything about the biconditional yet, but we're going to do that in the next video lesson. And for each of these, we have an introduction and we have an elimination rule for each of these. And I'm a little bit too lazy to write them all out. So why these, right? One of the things we noticed, for example, is we have, like in mathematics, if you have 1 plus 2, we notice that that's just the exact same as 2 plus 1. And some students notice that, well, wait a minute, conjunction is just like this, right? If we have a sentence A and B, then that's actually just equivalent, and we're going to use the biconditional actually here to express equivalence. But this is just actually equivalent to B and A, right? These two sentences are truth functionally equivalent. So whenever this one's true, this sentence will be true as well. So why can't we make that a rule, right? Why can't we say whenever you have A and B, then you can actually infer B and A? All right, so the schema might look like something like this. Whenever you have, oh, actually I need to use meta variables. So pretend this is Q and pretend this is P, these are meta variables here, these are any two sentences. So whenever we have these, we might be tempted to introduce a rule that says, okay, you can replace any sentence like that with a sentence of this form. So you're just flipping them around. And this is actually a perfectly good rule to introduce. But we don't have this yet in our system, right? Before we introduce a rule like this, we need to prove that that this is going to be a valid inference. And one way we could do that is using the truth table method that we actually just did. But there's another reason why we might not go about it this way. And the idea here is sort of a minimalist project. And that is, we're interested in figuring out what are the sort of minimalist rules that you need, and you're able to prove everything that can be proven using these connectives. In other words, one of the things that we're interested in is what's actually called, so let me just make a little bit of space right here. What we're interested in is this notion called completeness. Oh, I didn't want to grab that. What am I doing? Oh, jeez. There we go. Oh, man. I don't know what I'm doing anymore. Shoot, guys. Alright. Well, I'm going to have to start this over again, but let me see. Yeah, this is not working. Okay. Well, I'll cover some of that motivation in the next video.